Hi, so now we are in chapter 13 or chapter 6 in the custom RCC edition. And this is comparing three or more means. This is used for comparing three or more means. And we know actually from chapter 12 that we have the ability to compare three or more proportions. So naturally, we want to know how to compare three or more means, and that's where this comes in. Um, in chapter 13, we use a process called a one-way analysis of variance, or ANOVA, A-N-O-V-A. And I'm going to do things a little bit differently this time, which is start with a problem and show you how to do it on your calculator. So this process will only work or help you out if you're given the actual data and you have to calculate certain things involving comparing three or more means. So if you're not given the data, then you will want to focus on what I'm going to be talking about after this example. So let's start out, and I've already entered the data into L1, L2, and L3. That's what you want to do first. Um, so I'm already done with that step. That's what you'd want to do first, is make L1, L2, and L3 because we have three different populations. Okay, and then we would want to go over to tests and go to ANOVA right there. Analysis of variance. So then we want to do L1, comma, L2, comma, L3. So we are comparing those three different lists with this analysis of variance process. And very quickly we have a lot of information, and let's pull out certain pieces of information to show you what this means. So first off, we know that we have the top value, F. F is our test statistic. That's F sub naught. F sub naught is equal to 5. That is our test statistic for this data. And then the next thing would be our p-value, which is right below that. So that's the, you should have an idea of what that means, but it represents kind of how unlikely this would be to be um, rejecting the null hypothesis and being incorrect. So it's the area on the tail, as you know, in regards to the test statistic. So our p-value is 0.02168, blah, blah, blah. So, and then we have this thing going on. It's called, they call it factor, and then they have DF, SS, MS, and then we have error, and then the DF, degrees of freedom, SS, and MS. So, actually, all this information under factor and error is used to calculate our test statistic. So, actually, the steps that are needed to do that. Notice that MS, which under factor, which is known as the mean square due to treatment, the MS under factor, it's known as the mean square due to treatment. That's the MST. Okay, so our MST, I'll just say MST, um, MST is equal to 30.7 approximately. And then we have the MSE, the mean square due to error. MSE, that is equivalent to 6.14, 6.1, let's put 6.14. Okay, so approximately. And so these two values, the MS from the factor and the MS in the error, is used to calculate our test statistic. So that's equal to MST divided by MSE. And we'll get to that in a little bit of when we break down the calculations more. But as you can see, 30.7 divided by 6.14 would be 5. It might be a little off because I rounded the values. But yeah, so we would get that. So let's see. Let's see what else we have here. The degrees of freedom. We'll talk about how they get the degrees of freedom for the factor to be 2 and the degrees of freedom of the error to be 15. But it would, well, the error is n minus k, where k is the number of populations and n is the total amount of values. So there's 18 values, and then there's three different columns here. So that would be 18 minus 3, which is 15. And then the degrees of freedom that's calculated up in the factor area is 3 from the k, the number of populations, minus 1. So k minus 1. That's how they get 2 for the degrees of freedom under factor. So, and as mentioned, what's known as the total sum of squares, or the sum of squares for the factor and the sum of squares for the error. That's the SS for each of the 2 categories. Whoops. Let's pull that up again. The sum of squares for the factor and the sum of squares for the error is simply the mean squared multiplied by the degrees of freedom. Or you more want to think of it as the mean squared is the SS divided by the degrees of freedom for each of the categories. And we'll get to that when we break down the equation a little more. And what we'll be mainly breaking down is the SS. We kind of understand where MS comes from. It's SS divided by DF, but we don't really understand where the SS comes from. So we're going to be breaking down the SS. That's going to be the main thing we're going to be breaking down. So let's go ahead and do that. So we've gotten the degrees of freedom from the output, or not the degrees of freedom, the test statistic, and the degrees of freedom for the factor and the error, or what's also known as the total and the error, or the treatment and the error. It's many different ways it's kind of referred to, but anyways, that's kind of the output that we have here, and that's kind of the main calculation. The ability to be able to calculate this 5 value is kind of the longest process in this section. So let's go ahead and check this out. I'm going to go ahead and show you how we would calculate each of these values. So let's start out with the MST. The MST, or also the mean squared due to treatment, the MST is equal to the SST, which is the SS right there, 61.4444 for this example. And we're going to show how we get, and this is n minus k, divided by n minus k. And then we have well, we'll talk about that in a second. The SST is kind of the main thing we need to talk about. That's what we need to break down. We kind of see where the n minus k comes from. It's obviously n is the sample size and k is the number of categories or populations. So SST is calculated by is equal to the number of categories in the first, which is 6, and then multiplied by x1 bar minus x bar. And we'll talk about that, what that means in a second. And then we square it. So what you may kind of see here is kind of like a standard deviation in a way. And then we're going to do that for the next next one. Actually, we do that for all three of them. So what I'm going to actually do is just put I and I there. And we do that for all I1, I2, and I3. We're going to sum them all up. And then we're going to divide by k minus 1. Okay. Or not k minus 1, n minus k. Actually, it is k minus 1 now that I think about it. I'm looking at the wrong thing. This is k minus 1. K minus 1 because the MST, the factor, had a degrees of freedom of 2. That's right. I'm looking at the wrong one. So yeah, it is k minus 1. So let's go ahead and continue. And now we can see, we'll continue and notice that we're kind of unsure of what this x bar I means and the x bar. What is x bar? So x bar is the mean of all the values. So we would add up every single one of the values here, and that's x bar. So I would so I'll just say x bar is the average of all 18 values. All the values in all the sets, you just average them all out. That gives you x bar. And then we would want to find the average of each individual column, each individual population, or a sample from each population, the sludge, the spring, and the NO. And so we would do that, and we would gather 3 different, since there's 3 of them, x bar 3. So what we're doing is we're going to be, I really want to calculate these values. I've not done that yet. I might leave that up to you to kind of show, but the idea is we want to use this equation right here, the SST equation. The SST does not include this right here. What am I doing? The SST is just this right here. I was writing out the MST again. So the SST is just the summation. So, and then we would throw that on top of here, and then it would be dividing by k minus 1 to get the MST. So that's how we would calculate each of these. So for the first, N1 would be equal to 6, N2 would also be equal to 6, and N3 would also be equal to 6. You don't have to have the same values in here, but I mean the same sample for each. You can compare different samples with different sample sizes from each individual population. So it's no big deal there. Now the SSE, which we'll be getting to here, is I'm going to go to the next page. The MSE now. The MSE is equal to SSE divided by the degrees of freedom, in this case is n minus k. So the SSE is defined as n1 minus 1 times s1 squared plus the n2 minus 1 times s2 squared plus n3 minus 1 times s3 squared. So we're going to find the sample standard deviation of each of your different variables of the 3 different columns. You'll have individual standard deviations for each, sample standard deviations, since they're samples. And you have a sample size, so you'd have 6 minus 1, 6 minus 1, 6 minus 1. you'd calculate the standard deviation of each. And so this would be your equation for the SSE, okay? And the n minus k, once again, is 18 minus 3. So this would equal whatever the SSE is divided by 15, okay? In this specific example we're dealing with. And so let's go ahead and show. So based off of what we've talked about here and how we calculated the SSE and the SST using these equations, I'm actually going to break it down really quick again. The SST, since we have more room, I'm just back of it. MST is equal to SST divided by n minus or k minus 1. And the SST is equal to, which is the numerator here. So notice SSE is what we're calculating in the numerator there. SST is what we're calculating on the numerator there. The SST is equal to N1 x bar 1 minus x bar squared plus N2 x bar 2 minus x bar squared plus N3, and that's x bar 3 minus x bar, and then square that. I'll put a 2. We would want to square that. Anyways, couldn't quite fit it on there. So anyways, and remember the x bar is the average of all the values in all of the, like everything you calculate, all 18 values in this example. And x bar 1 is the sample mean. And let's just go ahead and do that. It doesn't take too long to calculate each of these. So it might be convenient if you remember if you want to do this. And the reason I'm showing you it broken down like this is because you'll need to do this process if you're given, I believe it's problem 4 on your homework on MyLast Plus. It actually gives you all the x bars and all the all the sample means and all the sample standard deviations from each population, and they want you and the sample sizes, of course, because we need those, and they want you to calculate the test statistic. You would have to use these equations. You can't use a shortcut like with your calculator. You have to use these equations to do your work. So that's why I broke it down like this, and it's also good to see where it comes from and why it works. And the reason you can kind of visualize why this works, and the general idea. I mean, if you remember, we're dealing with what we're measuring in regards to the differences. For most problems, we're on the numerator. You're dealing with what we're comparing. Like what we're comparing is the means in this case, because we're comparing 3 or more means. So the numerator, going back to the test statistic, I'll just write it down again. The test statistic is equal to MST divided by MSE. The MST is composed of a bunch of mean information, and we're trying to compare the means. So that makes sense why we would be doing that. Is we would be comparing, in this case, the standard deviation of the means, right? And then we would be dividing it by the standard error. And as you know, the standard error is comparing the standard deviations of each of those. So that's why the denominator, the MSE, is composed of comparing the standard deviations of each sample. So it kind of makes sense. This is just the way around of being able to compare 3 or more means. It gets just a little more complicated, as you can see, compared to comparing 2 means, and then obviously it's way more difficult or complex compared to comparing just 1 mean, like back in chapter 10. So just a general idea of how things are working here. This, of course, is SST divided by 2. And I wanted to go ahead and show you really quickly um, the values, and I want to plug in the values. So let's go ahead and do stat calc 1var stats. So I did, this is the 1var stats on L1. So as you can see here, our X bar, we want to pull out the X bar. I go to the next page. X bar from L1. So our X bar 1 is equal to 28.3, and our S is of 1 equals 2.8. I'll just say 0.5. Oops, 0.5. And then we can also do the same thing for stat calc 1var stats second L2. So that is, this would be X bar 2, since we did this for L2, and that is equal to 32.3. And then we do S2 2.16, and then we have X bar 3, and that would be stat calc 1var stats second L3, and we have 28.5. That's exactly, which is nice for rounding. No needed round in there. 2.429. Okay, so there we go. We have the values we need to calculate our sample, our MSE and MSE. So remember that our MST, actually let's just start out with SST. That's kind of where all the calculations are. So N1 we know is 6. And then we would, and there is actually one other thing we need to calculate, which is X bar, which is equal to, it's very convenient that you have the same sample size for each one, because of that, they would be weighted equally, each of these X bars, because there's 6 in each. But in general, you would be using N X bar I over all of N. You would want to use this equation to find the appropriate X bar. And they actually show you this equation on problem 4. I remember seeing that. And anyways, but I'll just show you using the equation. It won't make a difference, but it would be 6 times, let's actually clear this. 6 times 28.3 plus 6 times 32.3 plus 6 times 28.5, and then divided by the total n, which is 18. So 29.7 is our X bar. Okay, so we'll need that for this calculation right here. And because and as I was mentioning, it's kind of convenient. We have the same n for each of these, n1, n2, n3. We could have just averaged these 3 values out directly because they're weighted equally, and we would have got 29.7. But in general, you'll need to use this if you have different size n's for each. So SST is 6 times x1, which is, or X bar 1 is 28.3 minus, and then 29.7 squared, plus 6 times 32.3 minus 29.7 squared, and then plus 6 times 28.5 minus 29.7. So as you can see, we're taking the standard deviation, or at least the numerator of the standard deviation, since this is the numerator, of our means. Okay, and this would equal, and actually a quick shortcut. You could put 28.3 6 times into L1, 32.3 6 times in L1, and 28.5 6 times in L1. So you have 18 values in L1 containing 6 of these, 6 of these, 6 of these. And then just do one var stats and find the standard deviation. It'd be more convenient just doing it this way, because you get the complication of the degrees of freedom, which is k minus 1, and it doesn't really work out that way. So anyways, you just do 6 parentheses 28.3 minus 29.7 squared plus 6 32.3 minus 29.7 squared plus 6 28.5 minus 29.7 squared. So 60.96. And I remember this a value very close to this on our output for our ANOVA. And let's just check that really quickly. So it would be our factor SS, 61.4. Because of rounding error, I have a little bit off because I rounded all these values up here significantly enough that it, we're a few percents off of the actual value. This is the exact value because they used exact values. Didn't round anything. And I did. So anyways, I'm just showing you where it comes from. And anyways, the MST, of course, is equal to the MST would be equal to SST divided by the K minus 1. And that would be equal to SST, which is 60.96. I'll just use our values. It's kind of rounded, but and then K minus 1 is 2. 3 minus 1. Number of categories minus 1. And that's equal to 30.48. You can kind of just see that. Anyways, and as you can see, our MS here is 30.7. So we're a little bit off again. So because of rounding. So that's just how you solve the MST. And in regards to using the equation, this equation here to calculate the appropriate value, I'm going to leave that up to you using this equation. So it would be 5 times the sample standard deviation squared. So as you can see, so it would be 5 times this squared plus 5 times this squared, and then 5 times this squared. And then we would divide it by 15. So I'm going to let you do that on your own. And then you'll need to use these equations on problem 4 and maybe other problems, but some quick tricks. And if you have any questions, let me know. This is just, everything we've just gone over is just kind of breaking down the test statistic. This is all we've gone over is just the test statistic so far, and breaking it down, and which will be useful when you do your homework. In regards to making a decision, you'll need to let's see here. you'll need to kind of reference the book maybe, or I can just go over it really quickly. Yeah, so as you may imagine, how the how a hypothesis test would go, there are preliminary requirements which are mentioned in the book, and the requirements to perform a one-way ANOVA test. There's 4 checks. It's in a purple box on like the 3rd page of the chapter. There's 4 different checks where we have to have a random sample or randomized experiment of k simple random samples representing the number of populations we're dealing with. Like our example, we had 3. So each of those have to be random samples. And then 2, the k samples, the individual, the k different samples must be independent of each other. Okay, so that's just a requirement. And then number 3, the populations must be normally distributed. And so normally distributed is still a requirement here. And then also a requirement is the populations must have the same variance. So this is kind of difficult to tell, but I'll just show you what we would need to do. So we would calculate the sample standard deviations, because that's the best thing we can do. If we're just given a sample, the best thing we can do to compare the population variance is to look at the sample standard deviations we get. And what we would do to compare, and obviously they're not going to be exactly the same, so we can't just say, all right, they're not the same, it's a failure. There's a check, and on the next page after the 4 requirements, it mentions the verifying the requirements of equal population variances. So the check that you need to do is to make sure when you compare each of the 3 standard deviations, you take the smallest, 2.16. S2 is the smallest standard deviation. And then we would take the largest. The largest is S1. That's the largest standard deviation. Okay? And we would want to compare the smallest to the largest, or 5. And we want to make sure that that the largest sample standard deviation is no more than twice the smallest. And as we can see, it's obviously not more than twice than the smallest. And that is your check for number 4, if you're asked to do that. If we have equal variances, which is a requirement, we can compare the sample standard deviations and compare the largest to the smallest, and the largest cannot be more than twice the smallest. And that tells you that the variances are close enough to the same. And that requirement is met by doing that check. And so, yes, for requirement of equal variances for the populations is met by this check we've just done right here. Okay, so there's the 4th check. And then we can go into the null and alternative. And as you know, as you can imagine, if we're comparing 3 or more means, we would have H naught. In this case, since we have 3 different different categories we're comparing, we would want to make an inference on the population. So mu1 equals mu2 equals mu3. That's always a null, is equality between the whatever parameter we're comparing. And since we're comparing 3 different variables, we want to compare their 3 means. And similar to when we were doing proportions, remember we did P1 equals P2 equals P3. And it could actually be more, depending on the example you're doing. You can have like 4, 5, 6, however many means. But the alternative is always the same. It's the opposite of this. At least one is different from the others. At least one is different. If they're all the same, that would be the null. And the way that all of them, the opposite of all of them are the same, or just to make this false, not the opposite, but to make this false is that at least one is different. Then all of them are not the same. So that would be your alternative hypothesis. And then you would have an alpha, of course, and then you would calculate the test statistic, and we've exhausted that. So you can calculate the test statistic F naught, and now you would naturally want to calculate the critical value, and the critical value is very similar to how we would calculate the test statistic, or the critical value in the chapter 11 when we were doing standard deviations, comparing standard deviations. We dealt with the F distribution. We would use that table again, where we would have numerator degrees of freedom, denominator degrees of freedom, and the numerator degrees of freedom is based off the MST. So the degrees of freedom for the numerator, is the degrees of freedom of the MST, which is k minus 1. And then the degrees of freedom for the denominator would be equal to n minus k. So for our example, it was 2 and 15. So you would refer to those. Remember, using the F table, you would have to look up the degrees of freedom for each. The numerator for the, I believe it's the top, the row, which column you're using. And then the degrees of freedom for the denominator would be which row you're using to reference on the F table to find the critical value. And then you would reference the appropriate alpha. Okay, so go ahead and do that. And that would give you your test statistic. And then you would want to compare the critical value to the test statistic like you would always do. And the general idea is that if your test statistic is larger than your critical value, then we would fail to reject. Or we would, actually I don't know which one I just compared. It said if your test statistic is larger than your critical value, you would reject. Kind of the general idea, if you remember the shape of a F distribution, similar to chi-squared. Starting at 0. If your test statistic is out on the tail, this is the rejection region. And this is the fail to reject, H naught. Okay? So it's all kind of similar to what we've been doing before. And your conclusion's the same way. You reference your flow chart, and you do it just that way. And pretty straightforward, not too bad. Anyways, let me know if you have any questions, and you should be able to get through your homework on this. And yeah, good luck.